Hello everyone. So today we're going to begin going over section 3.3, which is about the derivative of trigonometric functions. So today is going to be a little about the review of pre-calculus 12, starting with the unit circle in radians, as you can see here. So we have, of course, in the inside here, the standard all student take calculus, which tells you which one of the three trig ratios are positive. So in quadrant 1, all three are positive. In quadrant 2, only sine is positive. And then in quadrant 3, tangent is positive. And finally, in quadrant 4, cosine is positive. And then we have our angles, of course, are in the second part in blue. And those are the angles in the first go round of the circle, starting with 0 and then going up by power 6, power 4, and going all the way around to 2 pi. And finally, the last part, the numbers on the outside in purple, those are the corresponding x and y coordinates for those angles on the unit circle. So the radius of this circle will be 1. And of course, the significance of this unit circle is that the x and y coordinates matches with cosine theta and sine theta if the angle in blue is the theta in question. And finally, one more thing of note is that tangent theta is equal to sine over cosine. Okay, so that's first part of the review. There's also a second part about the graphs of sine and cosine. That's what they look like. You would have seen them back in pre-calculus 12, of course. So it's just a reminder of what they look like. We'll be using them to determine the derivative of the sine and cosine function, respectively. You can also use the difference quotient, but it's a little bit more intuitive to use the graph. So that's why the graphs have been included here in the notes. Okay, so back in chapter 2, we talked about some trigonometric ratios limits that are easy to evaluate. So these three here, you will notice that you can actually use substitution. Right, so you can substitute in 0, sine 0 is equal to 0, cosine 0 is equal to 1, and tangent 0 is equal to 0. So those are pretty easy. And then the next piece is the special trig limits, and we talked about them back in chapter 2. And we basically use a combination of graphs and other results to show that the limit as x approaches 0 for sine x over x is 1, and likewise the limit as x approaches 0 for cosine minus 1 over x is 0. And those will be a little bit more important later on as we go through our examples. Okay, so we're looking at some special limits here. We have limit as x approaches 0 for sine 5x over x. Now you notice that we cannot apply the limit directly above because, of course, 5x and x are not the same. So what we're going to do is multiply both the numerator and denominator by 5. So of course, you can then rewrite this as limit as x approaches 0 of 5 sine 5x over 5x. Now, we can use the constant rule for limits to move the 5 in front of the limit itself in the numerator. So now, suddenly, inside the limit, the sine 5x in the numerator and the 5x in the denominator, now those match up. And of course, that is simply going to give us 1. So the limit is going to be equal to 1. So we have 5 times 1. Therefore, the answer to our question is just 5. Let's move on to the second example. We have here sine 2x over sine 4x. Now we don't have the x. In this case, we need 2x and 4x, so we're going to do something similar to example 1. We're going to multiply by 2x over 2x in the numerator. That's, of course, just 1, so that's okay. And likewise, in the denominator, we're going to multiply by 4x over 4x. Okay, now what happens? Well, in the numerator, we now have 2x sine 2x all over 2x. And in the denominator, of course, you have 4x sine 4x over 4x. Okay, so now, of course, the important thing to note here is that sine 2x over 2x and sine 4x over 4x, those two will give you a limit of just 1. And given our limit laws, we can kind of evaluate this limit by parts if we wanted to. So that's what we do here. So now we'll just have limit as x approaches 0 of 2x over 4x. Now, of course, then the x's will eliminate each other. So we really just have 2 over 4. And that's going to give us 1/2. Okay. Moving on to the next example. See, in this case, we have a limit as x approaches 0 for 3x over sine x. Now, of course, we can use the constant rule to move the 3 in front of the limit. That's what we'll do first. So we just have x over sine x. All right. And then we can rewrite x over sine x as the reciprocal. So we can rewrite it as 1 over sine x over x. And of course, that's useful because we know the limit x as x approaches 0 for sine x over x, and that's going to be 1. So now we just have 1 over 1, which of course is 1. So we have 3 times 1, which is 3. Okay, so next up we have another limit question. Tangent 2x over x. So that one is a little bit more interesting because we haven't dealt with tangent just yet. And it's not one of our special limits from above. So let's see what we do here. All right. So we're going to rewrite this as sine over cosine. So I have sine 2x over x cosine 2x. And just like before, we're going to use the same trick. We're going to multiply both the numerator and denominator by 2. So we can have the 2x matching in the numerator and denominator. So this will be limit as x approaches 0, 2 sine 2x over 2x cosine 2x. Now we're going to rearrange this slightly to make it a little bit easier for us. So we're going to arrange it as a product of 2 terms. The first term will be, of course, sine 2x over 2x, because we know that limit is easy to evaluate. And then multiply by 2 over cosine 2x. Now, the limit on the first part, of course, that's just going to be 1, just like in example A. Now, for the second part, in the product here, this, of course, we can use direct substitution. As x approaches 0, cosine 2x becomes 1, so that will just give us a 2. 2 over 1 is 2. So you can see that the limit would just be 1 over 2, sorry, 1 times 2, which is just 2. Okay, so from there, we can look at one more example. I had to change it because it turns out examples B and E are the same. So let's look at this one together. We're going to apply the same technique as in some of our previous question. We're going to multiply by 7. So the cosine 7x in the numerator matches the 7x in the denominator. And of course, if you have been noticing it, we will factor out the 7 in the numerator and put it in front of the limit. So we are basically going to be left with 7 times cosine 7x minus 1 all over 7x. Now, if you evaluate this limit, we'll just have 0. So we have really just 7 times 0, which of course is just 0. So some of the important result of what we just did are really just A and B, because we can generalize those pretty easily. Just going to write down what those are. And that is limit as x approaches 0 for sine ax over x is going to be A. And likewise, limit as x approaches 0 for some sine ax over sine bx is going to be A over B. And that's kind of a direct result of what we saw in example A and B if we just generalize the coefficients in each case. Okay, so it's important enough that we will put a box around it. Okay, so what this is really saying is we have used some special limits that involve trig ratios, and we made more special limits that involve trig ratios. Okay, last thing I'm going to show you today is using these two special limits, the ones that are from chapter 2 originally. So these two, we can show what the derivative of sine x and also cosine x, but we'll just do sine x today, using the difference quotient. But to do that, you need one more piece of information, and that is the following. I'm just going to write in darker red. So sine alpha plus beta is, of course, equal to sine alpha cosine beta plus sine beta cosine alpha. And of course, that's also from pre-calculus 12, and we have reviewed it. We have reviewed the trig identities already, so we're going to apply them here. Right. So how do we do that? Well, we're going to start with function f of x is equal to sine x. We're going to ask the question, what is then f prime of x? Okay. So we will apply the difference quotient. So f prime of x, of course, is the limit as h approaches 0. In this case, we have sine x plus h minus sine x. And it's all going to be over h. So from here, what we're going to do is apply the identity. Just going to move it a little bit to the left, so to give myself more space. So that, of course, will be sine x cosine h plus sine h cosine x minus sine x all over h. Now from there, there's a couple of rearrangement that will really help us out. The first one, of course, is to write the terms with sine x together, and we're going to separate the to two parts. So the first part will be, like I said, grouping the sine x's together. So we have sine x cosine h minus sine x. That's going to be divided by h. And then we're going to add sine h cosine x all over h. Oops. Uh-oh. Sorry about that. Let's see. Okay, let's continue for h. So now you'll notice that h is the variable that's being manipulated here. So in the first term, this part, we can factor out sine x. So we can rewrite this as sine x, and the limit as h approaches 0 of cosine h minus 1 all over h. And then the second part, we're going to use the limit law for sums here to separate for these two terms. We can factor out cosine x, and then we're just going to be left with limit as h approaches 0 of sine h over h. So what you notice at this point is that the first limit, this is equal to 0, and the second limit here, this is equal to 1. So the first term will disappear altogether, so this is all just 0. And the second term will just be cosine x multiplied by 1, which is cosine x. And that is to say that the derivative of the sine function is the cosine function. So you can do something very similar for the cosine function and find its derivative. We will not be covering that here. On the next day, what we're going to do is to examine this relationship between sine and cosine and the derivatives using graphs, and also to look at the derivative of the other trig ratios, so tangent, secant, cosecant, and also cotangent. But that's it for today, so thank you for listening.